Hello, everyone. Welcome to the user webinar. So I'm Matt Legler here at Cybernetics. I think most of you know me, and I'll actually be presenting today too. So let me share my screen and get the presentation started. I will tell you right now, though, that a lot of this is in PowerPoint, but I have a section in the middle that's marked where I'll jump out for a minute and show some stuff in Viewer. So let me get to the start here. Hello. What I'm going to be talking about today is pumping a seven-person murder mixture for TrueAllele information. And so what this involves is a case that we received back in, I want to say 2014, where we actually reported on a seven unknown. I'm also going to touch on genotype concordance during this talk, and that's actually what I'm going to show in Viewer. So that's the couple like main topics that I'm planning on touching on during this presentation. We'll also talk a little bit about validation. So the crime on the first slide now, just let me know if it didn't advance. So the crime was on April 7th, 2014. A person killed a gas station clerk during a robbery and then proceeded to rob the store. They had surveillance video. Just get zoom out of the way. And from the surveillance video, they could see that like he wore gloves. However, his arm might have came in contact with a register or the lottery slots whenever he was like taking all the money. Also, they noticed that it appeared that the suspect had a white plastic bag with him, which I've highlighted here because that's what we're going to end up focusing on. So from this, uh, this is a shot of that video surveillance footage showing the person. So based off of this, they did have a suspect. This was in Maple Heights, so this was a photo released by the police there. And from the scene, they collected several DNA samples, three of which came to us here at Cybergenetics for reasons I'll talk about in a minute. And so we had a gas pump button outside that probably saw I'm using that, the lottery cash register slot, and then the plastic bag that is going to be what we're focusing on once we get to the statistics. You'll see why. So this was initially had a previous analysis done. It was done by Cuyahoga County. However, this was in 2014. So this was before they deployed or validated TrueAllele. And so at that point, they were doing manual analysis. I believe it was a CPI. Lab can correct me if I'm wrong on that. And so this is just straight quotes from the lab report we received with the data. So they were able to cannot be excluded on the victim at a pretty high statistic. And so that's not super probative. He was on item 14, which is the cash register. He worked there, so that's not super helpful. And the gas pump and the bag were deemed inconclusive due to too many contributors. So the only match stat they had at that point was to the victim. So not particularly helpful. So the data then was sent to Cybergenetics. We were working with them then, so they were aware of us. And what I'm going to focus on here is actually the plastic bag data. And so this is at the bottom, we have a statement consistent with at least four, and then listing two markers, five, listing two more markers, or six or more contributors. And so this was actually a note copied from our analyst notes of what they saw whenever they were looking at the data. So what we see here is the example from FGA. Probably one, two, three, four, five, six, seven, eight, and then some baseline stuff. So there's four right there. Um, then looking at D2, we have even more peaks. So this is what they were pointing at for five. And then going over to D1, even more peaks. And so this is what they were pointing at for six. So there was some ambiguity about the number of contributors, just looking at the data. And so with TrueAllele, what we always say is if you're not sure, run it under multiple possible conditions, because whenever you do that, you'll see what best explains the data. Which we'll actually see in this case. I have a table later showing exactly like what that means. So then what was done here at Cybergenetics is we did trail analysis. We ran it at 4 to 8 contributors. We ran it at 100,000 and 200,000 cycles, which is probably a little bit long for reasons we'll see later when I talk about validation. But we tend to run things longer because we have more computers than people here. And then we also considered a degraded DNA option. And so that was the processing. So from that, we're going to obviously get a lot of stuff to look at. We have four, five, six, seven, eight, 5 different conditions, 2 different cycle sets. We replicate everything. So now there's a lot of data that we're going to need to review. And so then the first question is probably, okay, how do we do this efficiently? Well, one of the concepts that we really focus on is genotype concordance. And so here, just to make it something that is reasonable to show, I'm going to focus on the NCON7 request. So here, what we're going to have is we have 4 requests, 100K and a replicate, 200K and a replicate, each of which is producing 7 genotypes. We're telling the system to infer 7 contributors. So that's going to be 28 genotypes whenever I load it in the viewer here in a second. And the question is, how do we review this efficiently? This, I mean, I could open up the genotype with everything on, and you just see like a mass of bars, which is not going to be helpful. So what we tend to do is we use the match table, as I'll show, to help guide us. And then we use the built-in filtering of viewer to help guide us even more. And then what we're focusing on is, are these genotypes concordant with each other? And so that shown in viewer node at the bottom is my hint to go over to um, the viewer window. So you should now see I have the genotype selector. I'm using a TAS file to just load in the 17.1 item results. And let me make that a little bit bigger. Okay, so what we have here, just to clarify, you can see we have many shades of blue. And so we have 7 genotypes from the 100K, 7 more genotypes from the replicate of that, 7 more from the 200K, and then 7 more from the replicate. We then have 3 references. The main ones of interest here are 16, which is our victim, 20, which is one of the suspects. And then we have 3 relevant populations. So right there, we have 24 things here, 3 things there, 3 things here. So that's 9 times 24. That's like 200, over 200 match comparisons we're focused on here. And so obviously we don't want to look at all that. So what do we do? So we start with the match table, which is going to be a lot. And so we see all of these comparisons. And so then let's focus it a little bit. Let's turn off all the negatives. We're looking for inclusions here. Okay, so this tells me another bit of information. Looks like 22 is not in there. Looks like we're getting match statistics to both 20 and 16. Okay, so now let's focus a little bit more. I can go in and I can say over here in the subject reference, let's just focus on that suspect match. So I'm selecting 20, who's our suspect. And then down here, I could put in a cutoff and say only show me matches above a certain level, or I can just leave it blank, which is what I'm going to do. And then it's set to max within request based off of match. So what does that mean? So what that means is whenever I click the apply button, if I go over to the genotypes, the evidence genotypes, you'll see that it now has only selected four. From each request, it has selected the maximum match statistic to the one reference I have selected. So now when I come back to look at the match table, it's a lot it's a lot simpler to look at. So now what I'm seeing is I have four positive match statistics, a 4.4, a 4.9, a 5.2, and a zero point 0.1. So even from here, I'm already getting a sense of what looks, even just based on the match information, concordant and what seems like an outlier. Also, looking at the KLs, these are all fours and twos. This one's an eight. Over here, the mixture weights, 11, a 13, a 15, a 22. Again, the outlier here. And then the standard deviation, 6%, 6%, 8%, 0.6%. So this seems overly tight. So let's look at the genotypes and see what happens there. Let's start by taking out that outlier. So I'm going to turn off Q19, and I'm just going to focus on, and just for ease of use, I already know that the black population is the minimum match statistic, so I'm just going to leave that one on. Um, and now let's look at the genotypes. And so what I'll see here, once I expand the window, is I have a range of different allele pair possibilities here. And green is our reference. Blue is the inferred evidence genotypes, of which I have three right now because I turned that one outlier off. We'll come back to it. And then brown is our population. So what am I looking at with genotype concordance? Well, it's not that they are necessarily all on top of the reference or anything like that. Instead, what I'm looking across is like the pattern. Where are the answers landing? And so what I'm seeing here is that in general, I'm getting these groups of three, and they're all roughly the same height. There's a little bit of variation there. But like I'm not seeing, for instance, that the light blue is giving me like a high probability at 1313. And so these look roughly like the same pattern. And we'll have a counter example in a minute here. So just going through, not even really focusing on what the actual Leo pairs are, but more like the pattern, the distributions. I'm seeing, okay, there's bundles of three and they're all roughly the same height. That's concordance. There's variation in there, but again, it's always kind of generating the same pattern. Bundle of three, bundle of three. There's not like a big outlier here. And so if I step through the rest, we'll see that this trend continues. And so whenever we're looking for genotype concordance, that's kind of what we're looking for. Not even necessarily like individual numbers or anything like that, but just these groups that are all roughly the same heights. Now, let me just finish this. Now, what would it look like if we had, maybe less concordance? There's one locus is an outlier. That's fine. But overall, over the entire set of loci, the patterns hold. So what happens if we have something that is a little bit less concordant? So I'm going to turn Q19 back on. And so now we have the one that I just turned on is this kind of middle-ish blue. So the pattern of the blue bars always follows the ordering here. So the leftmost one will be the lowest number, the rightmost one will be the highest number. So this one that I just stuck in at Q19, second from the right, is the one we're going to focus on. And what we're going to see here now is that that does not follow the pattern. So here, sorry, one second. And I can even lower this confidence level just to zoom in a little bit more, which will be helpful whenever we're looking at this. Um, the patterns here. So what I'm seeing is that middle blue is sticking out from the rest. And also I'm seeing a lot of places where it's not following it. Like we see these divots here too. Boom. It's sticking out, sticking out, it's sticking out, it's sticking out. And the other important thing here is it's not happening at like one locus. Like we saw as we went through and kind of looked at it, that here, let me go down even a step further here. We saw as we were going through that like sometimes there's variation at like maybe a locus. Here it's happening almost all the time. I can see immediately like, okay, it's sticking out right there, right there, right there, right there. And so it's not following the general pattern of the other things. It's still, closer than something that is giving a completely different answer. But compared to the other three, I can always kind of see that like that is the outlier. And so those outlier patterns is why that one would maybe not be included in the concordance set. And so we can always see it just kind of not quite following with the rest. And so for genotype concordance, that's like an example of like less concordant. Like in particular here, you see, it's way out there. It put almost all the probability on one answer, and the other three are always kind of spread over the same answers. So genotype concordance isn't just about getting the exact same answer. There's always going to be variation. It's landing and generating similar patterns. And so we can see, for instance, over here that like it's a lot lower, it's a lot higher, whereas the other ones are always very close to each other. And I think that, yep, that's the end. That set. And so that's an example of good concordance and a little bit lesser concordant. And so that's why whenever we choose to report, what we would be doing is we would be focused on the three concordant. We would define those as a concordant set and say, these are the three I'm focusing on. I'm not worried about that point one. And it's not a matter of like I kicked it out because it didn't match the suspect. I kicked it out because literally I could look at those genotype patterns without the suspect even there and still be able to say, okay, that one is the outlier. So back to presentation. So with that concept of concordant sets, what I did is I wanted to answer another question that may be in your mind, which is, okay, so we're focused on NCON 7, but why are we focused on NCON 7? What happened to all those other requests, the 4, the 5, the 6, the 7-person contributor, the 8-person contributor? So what I did is I went in, I quickly looked at those sets of 4 at each contributor number and defined a concordant set. And once I did that, I then averaged the log likelihood ratio. So effectively, I had 4 possibilities here, and I defined a concordant set. What happened is most of the time, all 4 were fine. Sometimes I kicked one out, like we saw with 7. So it's either 4 or 3 match statistics being averaged here. And so what you will notice here is something that we first observed in, I believe it was 2015 in our current validation, where once you assume enough contributors, you're going to get more information. The genotypes become more informative, and the match statistics maybe also become more informative. And so we see that here, where 4 and 5 didn't really cover everything. We're only getting around to 2. Then once we get up to 6, now we're covering the actual number of contributors um, supported by the data. And we see that jump from 2s to 4s. And then these 3 higher assumptions, 6, 7, and 8, all gave around 4. And once we probably are starting to overassume, what we tend to do is we'll assume n plus 1. So if we think it's 7, we'll also try the one higher. And we see that that didn't materially change the answer, and that actually The highest match statistics came from the seven. And so these were all for references to all matches to reference 20, the suspect, but you would see a similar pattern if you looked at the victim matches as well. And so this is kind of showing what we demonstrated back in the current validation that once you assume enough, you're going to get the correct answer, and that over assuming only tends to maybe slightly decrease it um, as the contributors get spread out or subdivided. And once you have the right around what the data supports, you see a significant difference in the statistics. So you can see like four and five is too few, six, seven, and eight just right. Goldilocks thing. It's just right there. Um, and so that was something I observed while I was looking at this. So based off of that concept, the analyst in this case would then decide what to report on. And so this is just a clip from our case report in this case. Um, so we say, we considered four, five, six, seven, and eight. I can tell you that both of these match statistics came from an NCON 7 request. And we see that a match between the bag and the victim is about 224,000 times more probable than coincidence, and that a match between the bag and the suspect in this case, Slater Howell III, is 98,000 times more probable than coincidence. Um, and so the interesting thing about this is not only do we have match statistics, but it's on that plastic bag that the suspect was believed to have brought to the crime scene. And it's both the victim and the suspect on that same item. He could, argue if it was just him that, oh, well, I just had that bag on my person and like it had nothing to do with the crime. It just blew, it blew down the street and just happened to land at the murder scene. But it's harder to explain whenever you have the victim and the suspect in context on something like this. And so that was a useful probative example in this case. However, this is, the legal system. And so questions are going to come up. The court's going to ask you, why is it reliable? How can you report, seven? That's insane. No one could possibly do that. How can you do that? How can we report on that? Oh, getting ahead of myself. One other note here. This was done back whenever we were doing sampling to calculate error rate. I also used our current distribution interface to calculate error rates here. So this is the error rate for the victim match. The victim match again was 224,000, and the chance of a false positive is 1 in 2.7 million. And so this distribution would be the non-contributors. The green is where our match statistic lie, and we can see that that is not in the population of non-contributors. For the suspect, his match stat was 98,000. The error rate was 1 in 1.28 million. And again, see the large non-contributor curve. And then, excuse me, and then see our separated match statistic. And so just wanted to, I saw a question pop up in chat, so just wanted to address that since I'm here. And so the question is, so there isn't a big concern of you all ensuring that the cycle numbers are consistent when reporting and determining concordance. And no, we tend to look at maybe the same contributors together. But even then, like sometimes we'll look at across three and four contributors and define the concordant set across everything that we did. But like across 100,000 and 200,000 cycles, if they're concordant, they're concordant. It doesn't actually matter how long it ran. What really matters is did we run it long enough to reach the solution space to get concordant answers? So we will absolutely look at like 25K, 50K, 100K, 200K, and define a concordant set across that entire thing. Okay. So now back to where I was a minute ago. We're presenting this in court. The court's going to ask questions. How do you know it's reliable? How can we report on mixtures with more than five contributors, which some people would say is completely impossible? The answer is we're scientists. We've done scientific studies. We've done a validation. And in that validation, we've actually validated on up to 10 contributors. What validation is that? That validation was published in JFS in March 2020, um, and it's the validating TrueAllele interpretation of DNA mixtures containing up to 10 unknown contributors, which I will point out was a chosen as one of the noteworthy papers of that year. It was done with people from cybernetics and Cuyahoga, as we'll see when I talk about the results. And so I'm just going to briefly talk about that validation and how it enables the reporting in this case. To begin, what did we do? So we had a validation design where the concept was instead of just doing the typical, one into one to two, the three, that kind of thing, we wanted to look like casework. What is the mixture weights in casework? Well, it's random. It's just a random event where somebody deposits their DNA and they're not bleeding in perfect proportions of 2 to 1. And so what was done is a randomized design was generated where there was two, three, four, five, six, seven, eight, nine, and 10 person mixtures, and then it would using a computer we just randomly generated. So for instance, at 2 person mixtures, we had a 7822, a 6634, at three, 9451, a 553312. And so it was a random design that more closely represents casework. The other thing we did, and you'll see here that there is this designed row and then an observed row, and you'll notice that a lot of these lower contributors are in gray. Why is that? Well, one of the things that was noticed as we were processing this data goes back to that concept of, once you assume enough contributors, you'll get a better answer. And what we noticed is, sometimes with these very minor 0.5, 1% contributors in these high person mixtures, they're barely even in the data, or maybe they're not in the data at all. And so what we asked is if a person was looking at this data, how many would they say are in there? And so that's how we got that observed column of, okay, looking at this data, a person may actually think that there's 6 people there. And so we actually ran everything at both the design conditions and the observed conditions as part of the study to show how that changed things. And I'll have a slide where I'll talk about that further. So, general trend, what do we see? We go over our typical axes of sensitivity, specificity, and reproducibility. Looking at sensitivity, with 2 contributors, we saw that there was more match information. So along the horizontal here, we have log LR, and then the vertical is just what the count was. So among the 6 2 contributor match statistics, they tended more towards the 20s. With 6 contributors, we saw less match information. They tended more in the like 4 to 5 range. Why is this? Well, we'll get to that in just a second, but I'll tell you right now, it has to do with um, DNA amounts. However, main concept here is it's sensitive. It is able to pull out this information even whenever the contributor number increases. Specificity. So was done using the sampling method. So this would have been done where we generated like 10,000 random profiles, compared those to every evidence genotype in the study, and then graphed a distribution curve. Um, from sampling. And so what we see here is that at two contributors, there was more match discrimination where non-contributors are giving highly negative statistics. At six contributors, there's a little bit less um, match discrimination, which makes sense. At six contributors, you would expect the genotypes to be more diffuse, have more probabilities, have more allele pairs being um, assigned probability. However, we see that these are both very specific. We're not seeing, for instance, matches at five or six. We're not seeing a large mass of like false positives. Reproducibility. So everything was replicated. This ties back to genotype concordance, where, if the genotypes are concordant and look similar to each other, they're going to give similar match statistics. And so what we have here is along the horizontal, we have the one run and its match statistic, the log LR. Along the vertical, a second run and its match statistic. If they were perfectly the same, they would be a 45-degree line. This is a Bayesian system doing MCMC, so some variation is expected. So we see that variation in the blue dots, which is the two match statistics varying around that line. And what we'll notice is two, highly reproducible. Six, there's more variation. And so this touches on a concept that I know I've been asked about and talked with groups about, of that like negative, of that two band range, where like we want everything within two bands. It's not a hard rule, it's a guideline, because with a two contributor simple mixture, yeah, you want them within two because you don't expect much variation. With a six-person mixture, maybe that's a little bit more flexible because not everything is necessarily going to be within two band of each other, because there's some more expected variation at those lower numbers. And so it's more a guideline of like, if you see it within two, those genotypes are pretty concordant. If you see it further than two, then you can't just say, okay, it's within two. I don't even need to like focus on genotype concordance. It's more, okay, let's look at it. What are the genotypes trying to tell me? Are they still landing in roughly the same spot? Yeah. So strictly in casework, we're not looking at within two bands. We're strictly looking at concordance. And so we're just focused on, are they concordant? And part of the reason for that is that is this reproducibility? Oop, sorry. Which is that we expect there to be a little variation whenever there's two. We expect more variation with lower contributor amounts, with higher contributor numbers. And so that is why I'm kind of harping on genotype concordance, because that is really what the analysts here are focused on. They're just looking at the genotypes versus each other and saying, are they concordant with each other? Okay. Now, what we have here is a figure that originally came out of one of the earlier TrueAllele casework validations, an information gap in DNA evidence interpretation, published in PLOS 1 in 2009. And the reason why I'm showing this is this was actually figure one in and replicated in the um, 2020 paper. What is this showing? Along the horizontal is effectively the log DNA amount, 10, 100, 1,000 picograms of DNA. Along the vertical is the likelihood ratio, 1,000, million, billion, so on a log scale. And what we're seeing here is that this relationship is log-log linear. What does that mean? What that means is that the main indicator of what match statistic you're going to get from TrueAllele is how much of that person's DNA is in there. It's not just saying, okay, they're in there, give it a million. It's saying if there's a lot of their DNA in there, you're going to get, super high numbers, quintillions, sextillions. If there's a little bit of their DNA there, you'll get less support. Um, and beyond that, it's also predictive. This dotted line here was actually from described in this paper and was used in a case to show that, we knew from looking at the data that the person had about 67 picograms of their DNA in there. And so we would expect a stat of around a trillion. And that's what we saw. And so it was used to explain that like TrueAllele is predictable. It's not randomly giving high numbers, it's not randomly giving low numbers. It's giving an expected number, and that number is expected based off of how much of the person is in there, whatever, whoever we're looking for. Then um, one of the reviewers asked us to replicate this and show this linearity relationship held in this study. So here, obviously we only have less dots. There was only, six at two contributor, but the concept here is that linearity is still seen. So we're still looking at log DNA amount along the horizontal, and then log LR match statistic along the vertical, and it's still showing a linear relationship, whether it is two contributors or whether it's six. We see, more clustering because there's less of the people in the six, but that linearity holds. And so that was figure one from the paper there, and then also reflected in the different contributor amounts. I should also point out um, in the actual paper, I've been showing just because, you can only fit so much on a slide, the two endpoints, 2 and 6. Um, 3, 4, 5, these relationships for all this stuff, specificity, sensitivity, all of that is actually in the paper as well. Okay, so then let's get back to that concept I talk about of a designed versus a observed contributor number. So what we see here is in blue, the non-contributor distribution generated by sampling of the designed, so running it if it was a 10-person mixture, designed at 10, and then observed, which is looking at that 10-person mixture, a person would actually say there's 6. What do we see? And so what we saw here is that observed had more specific information, designed had less specific. What does that actually mean? So what's happening here is that there's an excess amount of contributors whenever you're going for like a 10 that maybe are not supported by the data. Whenever you do that, what happens? Well, you get very diffuse profiles that don't have a lot of information, very low KLs. And so since you have these uninformative profiles, you see them as this excess here in blue. And so that's why it kind of like stacks up against the 0, because these are the uninformative profiles. Because really, if you look at the data, there's really only peaks that can support 6. And so that's the main difference here, is just that if you over assume, if you were to take a 2-person mixture and assume 8 people, um, then what would happen is you'd probably get 2 informative profiles and 6 that have a very low KL. And so that's what's going on there. One other thing covered in the paper, peeling genotypes. So peeling or genotype conditioning is the concept of using like an assumed known. This is highly useful in cases where you have many, many contributors. And so that's what's going on here, is that we have this 10-person mixture. We assume nothing. And what we saw was stats ranging from 7 to 0.1. Then what we could start doing is you assume the highest match statistic. So that would be suggested to be the most informative profile there. And effectively what we're doing is we're peeling it away layer by layer. So the next row over, we assumed 1 person indicated by the K, and we see that increase in match statistic. Then whoever's the highest, you assume them, and rinse and repeat. And so what we can see here is the impact of that, particularly on this 15% contributor here. We went from a 3.2 when we only had one or zero thing assumed knowns up to an 8.4 whenever there's five. We also noticed that for some of them, it doesn't make much of a difference, but for some, it makes a significant difference. So this is how we tend to deal with cases with large number of contributors or cases where maybe there's a lot of family relation. Uh, we had a five-person family mixture where everyone was related. The way we dealt with it is something like this, where you go in, find whichever family member is there most informative, peel with them, see what happens to the other um, profiles. And so it's just a sequential um, round after round of processing. So this is 6 rounds of processing, 7 rounds of processing. Look at it, peel one, whoever's the next, and so on. Then, an interesting question, definitely for groups where you have more people than you do computers, is how long do I need to run things? So in this validation, we actually ran everything under multiple conditions. So what you'll see here is this is actually 1,000 cycles, 5,000, 25,000, 50,000, 100,000 cycles. And this was for a five contributor mixture. Longer sampling tended to give better metrics, convergence, that kind of stuff. However, what you'll notice is that at one, and so what we're seeing here is sampling is along the horizontal, and along the vertical is the log likelihood ratio match statistic, where each line, each different colored line is a different contributor. And so what you can see is, and then there's whiskers around them that show like the variation amount. And so what we see is that there's a lot of variation and a lot of movement at 1 or 5. And then once we hit 25K, that tends to be enough. And we go from 25 to 50 to 100, and there's not any significant changes. Does that mean that we always run everything at 25K? No. Sometimes if you're trying to dig out the most minor contributors, you do need longer running. But for a large proportion of your data, if you're doing simpler mixtures in TrueAllele, you don't need to start at 50 or 100. You can start at like 25 and still get reasonable answers. How do you know it's a reasonable answer? Genotype concordance. You run it more than once. Are the genotypes concordant? If they're not, then maybe that means you do need to run it longer because there's more variation to map out. Or maybe you just do another 25K run and see if you can get a tiebreaker. But the concept is that for simple stuff, you don't need to start at 50. You can start at 25. That seems to be sufficient. And then last but not least, from the validation, independent testing. Cybergenetics made the software, and clearly we're the only ones that can run it. No, that's not true. Uh, what this shows here is that for this validation, Cybergenetics along the horizontal, we ran it. Cuyahoga also ran it. They did their own replicates of what we processed, and then we just mapped them out and said, okay, are we reproducible with each other? Are two labs across the lab reproducible? And so you can see that it gives a reasonable reproducibility, and it's right along that diagonal line. It didn't matter if we ran it or if Cuyahoga ran it. Cybergenetics is not the only one that can run the software. Other other groups can run it and produce the exact same answers. If you were to, you know, have multiple labs, they're all going to have very reproducible answers. And so that is independent testing. And so that kind of sums up all the things in the validation. The main concept here is that the system was validated on up to 10. We could point to this whenever we're testifying about it, and we have scientific support. So, testimony. Back in September 7th, 2017, DNA analyst Jennifer Bracamontes, who was Jennifer Horniak then, who is also the author on this validation paper under Horniak, testified about these computer results before a Cuyahoga County jury. Um, I talked to her about it. She said there wasn't anything particularly exciting about the testimony, even though the results, even though we're reporting on a seven-person mixture. And then what did she present? So these are two slides actually drawn from her visual aid in that case. And so these are a summary of what we found. Our victim, we saw neither on the gas pump button, on the cash register, which, I mean, he works there. That's that stat. We replicated what Cuyahoga saw. And then the probably most probative thing here, DNA wise, that that plastic bag. The victim's there at 224,000. The suspect it was there at 98,000. They're both in context on that item. This is the number of zeros. So five ban, almost five ban. Um, they're both there. And so that was presented. And then the outcome was, let's see here. Jen testified on the 7th. 5 days later, on the 12th, the jury found Slater Howell III guilty on all charges. Um, in November, he was sentenced to life in prison for that homicide. And then he also pled guilty to a murder charge that he was also associated with of a Cleveland firefighter. Um, if you want more details, there's a story still up about it on Cleveland. The main motivation behind these crimes was that it was gang affiliation. And so he was earning his bones. Um, and so he was probably, not going to stop it too. So it was good to, find information even from these complex mixtures. So to wrap up, the plan is that next month, Dr. Nasser Butt from the Cuyahoga County Regional Forensic Science Laboratory, who has since brought on TrueAllele, is going to discuss their workflow. Some of those things I said about 25K, that's how they process. And he's going to also probably talk a little bit about like how they're using a database and that kind of information. So with that, I can open it up if anyone has any questions.